Consider a force F that makes an angle alpha with the x-axis, projecting it on the x-axis to get Fx, which is the x component of the force, and here it's represented by a green vector, and projecting it on the y-axis we obtain Fy vector, which is the y component of F. Trigonometric relation, we have in a right triangle cosine alpha equal adjacent over hypotenuse, it's Fx over F, then Fx equal F cosine alpha. Alpha belongs to the first quadrant, so cosine is positive and F, the magnitude of a force, is positive. So positive times positive is positive. Now sine alpha equal to opposite over hypotenuse. Opposite here is equal to Fy vector because this is actually a rectangle and opposite sides in rectangle are equal. So sine alpha equal Fy over F. Fy equal F sine alpha, positive sign, so it is positive. Consider another vector, t vector, which is represented by the purple vector here, t vector, projecting it on the x-axis, projecting it on the y-axis in order to obtain the x component and the y component. So here we have that t makes an angle beta with the x-axis. So cosine beta is adjacent over hypotenuse, it's tx over t. And sine beta is opposite over hypotenuse. The opposite here is equal to ty over t. So ty equal t sine beta. And concerning the sine, t is positive, cosine beta in this case is negative. So positive times negative is negative, and this agrees with the representation. We have tx directed in the negative direction of x. And ty is t sine beta, t is positive, sine beta is positive, and positive times positive is positive. Now, how do we use these rules? Application 3, the following exercise could be given in two different ways. The first way is that we are given the magnitude of the x component and the y component of the force and the displacement. To determine the work done by the force F shown in the adjacent figure, knowing that the distance covered by the block is 4.5 meter. So F is usually expressed as Fx vector plus Fy vector. So the work of F is the work done by the x component plus work done by the y component. Work done by the x component is Fx times d times cosine 0. Y cosine 0, the angle is 0 between Fx and d vector because they are parallel and in the same direction. So 15 times 4.5 times 1 is cosine 0, it's equal to 67.5 joule. However, the work done by the y component of F is Fy times d times cosine 90 because as you can see Fy is perpendicular to the displacement. So 20 times 4.5 times 0, cosine 90 is 0, so equal to 0. Now the work done by the force is the sum of the work done by the components, it's equal to 67.5 joules. The second way is that you may be given the magnitude of the force itself, the angle between the force and x-axis, and the displacement, so you can directly apply the rule. Work done by the force is magnitude of the force times d times cosine 55. So doing the substitutions, we obtain 64.52 joules. Why did it differ slightly? Because we only considered 3 digits after the decimal point, so that's why it differs a little bit from the first way.